All right, so the second skill we're going to learn this unit is linearization. So let's just begin by talking a little bit about graphs that are linear and what we can get from them. So when we do have a linear graph, there's really a lot of information we can get from that graph. The first thing is we can determine the slope, of course, and that tells us how the y value changes as a function of x, the rate of change of y with respect to x. So that's the first thing we can get from it. The y-intercept's another useful thing we can get from the graph. And what that really tells us is, what is the value of y when x is 0? For example, if the x-axis is time, it would tell us the initial value at time t equals 0. Whatever y value, whatever's on the y-axis, it would tell you that value at time t equals 0. And lastly, the r squared value. This is something that I always ask you to get when you make graphs for this class. And what that really tells us is how well the data matches the best fit line that we've created. So there's a lot of stuff we can get from a linear graph, and linear graphs are really useful. But not every relationship is linear. We won't always have a linear graph. So the question is, what do we do when we have a nonlinear graph? So what do we do when we have a nonlinear graph? Well, we have a few options. We could take that nonlinear graph and try and do a lot of the same analysis. However, it's a lot harder to distinguish between similar nonlinear graphs, for example, x squared versus x cubed. It's harder to get that rate of change. There's a lot of things that are harder about working with a nonlinear graph. So our other option, the thing that we're going to do in this class, so we're going to use a technique known as linearization. All right, and that's the process by which we take a nonlinear graph and turn it into a linear graph. So let's think for a sec about an example. Suppose we have a graph y equals x squared. You all know that that will form a parabola like that. Obviously not a linear graph here. So what we're going to do is we're going to take this nonlinear graph and we're going to change what we graph. We're going to change what we put on the x and the y axis. And rather than putting x on the x-axis, we're actually going to graph x squared. Okay? And the reason we're doing that is if we put x squared on the x-axis, then our graph here becomes y equals 2 times what is on the x-axis. That is no different than y equals 2x. Okay? And so by changing what we graph, we're able to take this nonlinear graph and turn it into a linear graph. So let's take a look at exactly what that looks like. So here we have an example with some actual data. We have data on the number of apples compared to the number of oranges, and we see that that ends up forming this function here. That clearly is not linear. It looks parabolic in nature. And if we look a little bit closer at the best fit line, the equation of this best fit line, we see that it is parabolic in nature, and it's approximately y equals 2x squared. Obviously, it's real data, so it's not going to be perfect, but it's about y equals 2x squared. We see the 2 coefficient out in front, and we see that it's raised to the 1.99 power, so basically the second power. So this is the function that we were talking about on the last slide. So what are we going to do? We're going to turn this into a linear graph. All right? And the way we're going to do that is rather than graphing apples here on the x-axis, we are going to graph apples squared. And we're going to take a look at what that does, all right, on the next slide. But that's going to take this nonlinear graph and turn it into a linear graph because now this entire piece, including the power, is our x-axis. And so really it's y is equal to 2 times whatever is on the x-axis, and that ultimately is a linear graph. So we can see here, here's our modified data. We've taken all of those apples values from the last data table and we've squared all of them. And when we do that and regraph it with apples squared on the x and oranges on the y, you clearly see that we now have a linear graph. Okay. We have a nice r squared function, and here is our new equation for that line. So let's now dive a little bit deeper into this and actually analyze that best fit line, that r squared value, and get some information from it. So looking at that equation and r squared value, which I have up here, let's go ahead and analyze what we can from that. So the first thing that we can say is that the number of oranges is proportional to the square of the number of apples. And that just came from the fact that the way we linearize this is by putting apples on the y-axis, or oranges on the y-axis, and apples squared on the x-axis. And that's what leads us to say that oranges is proportional to the square of the number of apples. Second thing we can say is that because our slope is about 2, 1.995, that means that the number of oranges increases at a rate of 2 oranges per apple squared. Okay, so every time the number of apples squared goes up by 1, the number of oranges goes up by 2. All right, and so that's what we can get from the slope. And lastly, the y-intercept here is basically 0. We see that it's 0.0923, which is significantly smaller than any of our y values. So it's safe to say that the y-intercept is 0, just with a bit of uncertainty. So when there are no apples, there are also no oranges. Lastly, if we were trying to justify the quality of our data, we could turn to that r squared value and say, well, it's an r squared of 0.99. That shows that this line is a very good fit. If we had gotten a bad r squared value, that would mean a few things. It could mean that our data is just not great. It also could mean that we didn't properly linearize it. We still weren't really at a linear fit, and maybe we need to adjust how we went about that linearization. All right, so a few tips here for linearizing. We first want to determine what relationship we have mathematically, and that's going to come from two things. We can either look at what I would refer to as the original graph, like the graph we saw before we linearized the oranges to apples example, or there will be times when, and we'll talk about this later on in the unit, when you have an equation that is known and you're trying to prove something through the slope, through the y-intercept, etc. And so you'll actually have an idea ahead of time before you even take data of ultimately what you're going to need to do to linearize that data. So sometimes it will be starting with a known equation. Other times it will just be a matter of looking at the data and based off of the shape determining how to linearize it. Once we figure that out, we want to isolate the dependent variable, whatever is on the y-axis. Okay, that's the next step. And then we're going to change one of the axes. I usually try and change the x, but you can change the y-axis as well to match what the known relationship is between the y and the x. All right, so we're going to modify our axes to take that nonlinear graph and turn it into a linear one by graphing something different on the x and y axis. So there are many possible functions we can have between two variables. There are many possible graph types that we can have, but there's a few that you're going to be responsible for knowing. There's a few that I'm going to expect you to recognize. The first, of course, is a linear one. You all know what a linear graph looks like. The equation is going to be y equals mx plus b, where m is the slope, b is the y-intercept. Obviously, we don't need to linearize a linear graph, all right? But you still should know the form of that function. Second graph we're going to deal with is a square root graph. A cube root or some other root would also look similar. We're not going to get too much into that. Again, we're going to kind of simplify it to just 4 different types. So anyone that curves like this, that's concave down, something like that, but increasing, that's going to be indicative of a square root graph, which takes the form y equals k times the square root of x. We could have a y-intercept as well, but the important part is going to be this piece right here, that it's a constant times the square root of x, because that's going to tell us how to linearize it. The next graph we're going to deal with is a quadratic graph, which takes the form y equals k times x squared. Again, you could have a y-intercept added on here, but the important piece is that the x value is squared. That one, you know what it looks like, your classic parabola, concave up and increasing, all right, something like that. This is technically half of the parabola, the other half would be over here, but oftentimes we're not going to be concerned with the negative x values, because our x-axis a lot of times will be either time or mass or distance or something where it doesn't really make sense for it to have a negative value. So parabolas are really just going to be half of a parabola. But when you see a graph that looks like this, could be a number of things, but for this class you need to know and recognize it's a quadratic and know how to linearize that. And then our last function is one that looks like this. As the x values increase, the y decrease. This is an inverse function. It takes the form y is equal to k, a constant, times 1 over x. Okay, so when you see that, that's what you want to think about in terms of that linearization, that it's 1 over x is what has been done to that x value. All right, so let's take a look at this first practice problem. We have a data table here showing time and height. Although it doesn't explicitly say this, I'm going to assume that time is the independent variable because it's the first column listed, and height is the dependent. So I'm going to go ahead and set my scale here and then graph this function. And we're going to take a look at what it looks like and then ultimately determine what the proper linearization should be. Alright, so I now have my points plotted. I went with every 2 was 1 on both axes. That seemed to be a good scale. I went and plotted my points. I'm going to draw my best fit line now. Remember, we're not necessarily connecting the dots, but trying to just hit that general region. And so what I see is a graph that looks like this, where it is increasing, but looks like it's concave down, at least to some extent, which indicates to me that this is going to be a square root graph. All right. So what we're going to do is we're now going to take the data we have, and we're going to linearize it and change around this time axis to be the square root of time. Okay. So whatever has been done to the function, okay. If it's a square root graph, we're going to square root the x-axis. If it's quadratic, we're going to square the x-axis. So since it's a square root, we're going to graph the square root of time on the x, and that should lead to a linear graph. So the first step is going to be to modify my data here. So instead, I'm going to have the square root of time in units of square root of seconds, by the way. And then the height's just going to stay the same. So I'm going to go ahead and do those calculations and fill in this chart with my new data that I'm going to graph. So I've modified my data. The heights are exactly the same as they were before. The times, though, I've taken the square root of each of those times from above, square root of 1, 2, 3, 4, and so on. What we're going to do now is we're going to graph this data, and we should find a linear graph. Alright, so now we have our data graph. You'll see I changed the scale on the x-axis. Each block is 0.2, so 5 blocks is 1. And then on the y, I kept the same. Notice that I don't necessarily write in the numbers for each individual one, but I will do it every so often just to make it easier for graphing purposes, and that's totally fine if you do the same. We're now going to go ahead and draw our best fit line. Alright, so we're going to start there, and our best fit line would look something like that. And from that, we're going to determine our slope. Now, when we determine our slope, we want to make sure that we pick points that are on the line itself. That may mean that they're not the same as our data points here. These do not necessarily fall on the graph, so we don't want to just blindly pick points from there. We want to find ones on the line itself. So this first one here I have is 0.6, comma 1. That's one good data point, and then we want to pick another one that's far away. This would be another good data point right here, and that's going to be the data point 2.8, comma 5. All right, so those are the two data points I'm going to pick, and I'm going to use those to find my slope. So slope is change in y over change in x, so 5 minus 1 over 2.8 minus 0.6, and so what we end up getting here for our slope is 1.8 as our slope, and we want to add in the units, so it's going to be the units of the y-axis, which were meters, over the units of the x-axis, which were the square root of seconds.